Okay, so it's been a little bit of time since we've looked at some maths calculations with our chemistry, and with pH we do have a couple of calculations and formulas that we need to be able to use, so let's get straight into this. Remembering that while we're using logarithms in this, we're not expected to be able to rearrange logs comfortably. If we just memorize the two equations, it will be fine. So for the most of this, it's just remembering which values you need to plug into your calculator. Don't let it freak you out. So let's get started. So in our last video, we talked about the ionization of water and how that pH is determined based on the concentration of H3O+. So anytime we use the pH equation, if we're using pH, then we need to be using the concentration of hydronium. Okay, so we need to be able to get it in terms of concentration of hydronium at all the times. We've also talked about the fact that water will self-ionize. It's an amphiprotic substance, and that water, when in solution with more water, okay, in a water liquid, is actually constantly bumping into each other and swapping protons. So we're getting a mixture of H3O plus and OH minus in low concentrations in solution. The amount of this that occurs in solution is known as the ionic product of water, or the ionization constant of water, okay, which is given here. Kw is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions. This is a constant. It is given in your data booklet, so you don't need to memorize it. It does have the value, as we see down here, of being 1 times 10 to the negative 14. This is because you may remember we said in pure water, the concentration of H3O plus was equal to 1 times 10 to the negative 7. We also said that in a neutral solution, the concentration of H3O plus is equal to the concentration of OH minus. So if we multiply these two values, okay, because if they're equal, then the concentration of OH minus is also going to equal 1 times 10 to the negative 7. Then as you can see down here, when we multiply these two values together, we sum the indices, and what we get is 1 times 10 to the negative 14, and this has a rather weird unit called molar squared, and we'll look at that more in unit 3-4, how these constant units turn up. But at this point in time, the main thing you need to know in year 11 is that at 25 degrees C, when we multiply the concentration of H3O plus and OH minus together, we get 1 times 10 to the negative 14. This applies to pure water and aqueous solutions, and we call this the ionic product constant, or the ionization constant of water, Kw. Okay, so this is just a value that you need to know. If you think about this, it means that if you know the concentration of OH minus instead of the concentration of H3O plus, we can solve for the concentration of H3O plus by substituting in this value here. Okay, so it gives us a way to always find the concentration of H3O plus. So in acidic solutions, we talked about the fact that H3O plus ions are formed, and also with the reaction of acid and with the ionization of water molecules. So the concentration of H3O plus is greater than 10 to the negative 7 in an acidic solution. In a basic solution, this means that the concentration of OH minus will be lower than the concentration of H3O plus. It's going to be less than 10 to the negative 7. Okay, so H3O plus is going to be less than 10 to the negative 7 molar, and OH minus concentration must be greater. Remembering that we have this situation where this is like a seesaw. If one goes up, the other has to go down. Okay, so that's what's happening here. So the higher the concentration of H3O plus, the more acidic the solution is. The H3O plus concentration can range from 1 times 10 to the negative 14, okay, to 10 molar concentrated strong acids. Okay, so indicators are substances that are going to change color at specific H3O plus concentrations, and we have used these in the laboratory. Most often we use universal indicator, but there is a large range of indicators available to us. Due to the huge range of H3O plus values, the pH scale has been developed to measure acidity. And we talked before in our last video how each step on the pH scale is a ×10 difference in concentration. So in order for us to do calculations to determine the pH of a solution, these are the formulas that we must know. There is our constant, Kw, the self-ionization constant of water, which remember is H3O plus concentration multiplied by the OH minus concentration is equal to 1 × 10 to the negative 14 m squared. This is our pH equation. pH is equal to the negative log to base 10 of the concentration of H plus or hydronium. This is the one that we are going to see how to use today. And then this is the arrangement of this into from its log form. So the concentration of H3O plus is equal to 1 × 10 to the negative pH. Okay, so this is going to be one that we need to use as well. Okay, so a key thing to remember though is that we cannot solve for the pH of solution if we don't have the H3O plus concentration. We cannot substitute anything into this equation other than H3O plus. Okay, nothing else. So this again just goes through the range of pHs. So if the concentration is greater than 10 to the negative 7, it's going to be acidic. If the concentration of H3O plus is less than 10 to the negative 7, then it's going to be basic. And if they are equal, they are neutral. So let's have a look at a couple of sample problems so you can see how this goes. Starting with looking at finding out the concentration of hydronium. So we're told here to calculate the concentration of hydrogen ions in blood if the pH of blood is 7.4. In this case, we have been given the pH. We want to find the concentration of hydronium. Okay, so we can use the fact that, remember, concentration of H3O plus was equal to 1 × 10 to the negative pH, or 10 to the negative pH. So in this case, it's going to equal 1 × 10 to the negative 7.4. We're going to place this into our calculator. Okay, you should not leave it here. Don't leave it here. Okay, you need to go through, put this into the calculator. So you're going to just put 1 × 10 to the negative 7.4 is equal to, and you should end up with 4.0 × 10 to the negative 8. This is a concentration. It is a molar concentration. So our unit for concentration is going to be molar, or moles per liter. Okay, so that is our first example of how we can calculate pH, calculate hydronium concentration given the pH. And that's just it typed out. So let's look at this one. So now we're looking at something where we have a 40 ml solution of 0.2 molar hydrochloric acid. So we have a volume. Careful to note that it's in milliliters. 0.2 molar hydrochloric acid, so we have a concentration, and it reacts with 20 mils of 0.1 molar sodium hydroxide. Calculate the pH of the resulting solution. So what we have here is a reaction occurring. Okay, we are adding hydrochloric acid plus sodium hydroxide. Okay, so we have an acid plus a base. So this is going to be a neutralization reaction, and it is going to give me salt plus water. Okay, so I have 40 mils of 0.2 molar hydrochloric acid and 20 mils of 0.1 molar sodium hydroxide. I will get 1 HCl neutralizing 1 sodium hydroxide. Okay, the only way I can compare amounts in chemistry is to determine the number of mole. So what I'd like you to do is pause this video, calculate the number of mole of each of them, and then come back and we'll look at the solution. Okay, hopefully you paused and did the calculations, but let's have a look at these in a bit more detail. As we said, we have a reaction that is occurring. We have HCl reacting with sodium hydroxide to form sodium chloride and water. If we use N is equal to CV, okay, which is our concentration equation, and we can find the number of mole of HCl, this will take our concentration. This is our concentration of HCl, and this is our volume, remembering that we have converted our volume to liters. That will give us 0.0800 moles of HCl that was placed in the reaction flask. Doing the same for sodium hydroxide, we get 0.1 molar, this is our concentration, multiplied by our volume converted into liters, will give us 0.002 moles. From the reaction, we can see that it's a 1:1. We will get 1 mole of HCl neutralizing 1 mole of sodium hydroxide. So if we want to have a look here, we have 0.008 mole of hydrochloric acid and 0.002 mole of sodium hydroxide. The sodium hydroxide will neutralize this amount of HCl. Okay, so if it does, then that means I will have my initial amount of HCl minus what reacted, and this is what is left over. Okay, so this is the number of mole of HCl that is still in solution. Okay, now in order to work out the pH, I need to know what the concentration of that's going to be, because remember, if HCl ionizes with water, I will get H3O plus Cl minus. It's another 1:1 ratio. So the number of mole of HCl is going to equal the number of mole of H3O plus. So if I can work out the concentration of HCl in my solution, I'll know the concentration of H plus. This means I had 0.006 mole of H plus, but now I'm looking at the total volume of the solution because we added 40 milliliters with 20 milliliters. The total volume of the final solution is going to equal 60 milliliters, okay, or 0.06 liters. So my number of mole of H3O plus is going to be equal to the number of mole of HCl that was left over, okay, and I'm going to divide by my volume. And when I get that, I get a concentration of 0.1 moles per liter of H3O plus. I can now substitute that in to our pH equation and just type into my calculator negative log 0.1 is equal to, and my pH is equal to 1. This is a very complicated question. There are many steps that require to use your concentration understanding as well as the pH equation. This would be the most difficult kind of question that you would see at this point. Okay, next one that we're going to look at is looking at how they may be presented when we're talking about the pH of solutions, but we only know that we have a base. If our pH calculation only allows us to add in the concentration of H3O plus, I need to be able to find my concentration of H3O plus to be able to find my pH. So this means that in this case, whenever we are presented with a base, we need to remember that the Kw, which was equal to the concentration of OH minus multiplied by the concentration of H3O plus, is equal to 1 times 10 to the negative 14. Okay, which means I can rearrange this to find H3O plus is going to be equal to 1 times 10 to the negative 14 divided by the concentration of OH minus. Okay, so now I can find an unknown hydronium ion concentration that I can then put into my pH equation as long as I rearrange this formula. Okay, so let's see how we go. Pause this video, have a go and see if you can find the concentration of hydronium for each of these bases based on using this equation. Okay, so hopefully you were able to find those out. And what we had to do here was to take our concentration of sodium hydroxide, H3O plus, is equal to 1 times 10 to the negative 14 divided by, and remember to keep it in brackets when it's on the bottom, 3.34 times 10 to the negative 5. Okay, when you do that, you will end up with a concentration of hydronium, which you can plug into the pH equation. What I did want to point out to you is there is actually an easier way to do these, and that's using the idea that the pH plus the pOH is equal to 14. Okay, pOH is where we take the negative log of the OH minus concentration, and that will give us pOH. So if I want to find the pH and I've been given the concentration of hydroxide, I can say it's going to be 14 minus the pOH, and I'm just going to substitute this value into my pOH equation. This is not often seen in VCE, but it is an easier way to do it. When we're in class, I'll take you how to do both of them, just so that you are able to use the calculations in the expected way. We will be doing a lot of practice for these calculations in our next couple of lessons. Make sure you read through the chapter and in our textbook and have a go at some of the questions to consolidate this information, and I'll see you in class.